Howdy everybody. So what we're looking at today is how do atoms respond to electric fields. And the big picture that we're going to be keeping in mind today is a ball, something like that, which has this electron density and it has a nucleus, positively charged there, and this negatively charged cloud all around it. And we want to say, if we expose this to some electric field, let's say oriented this way, that's an E for all of you illiterates, you have then the new picture. What would it look like? Electron cloud with a slightly offset. There is sort of our center point. There's our new nucleus position. That positively charged nucleus is going to get pulled a little bit that way. So hopefully this X doesn't confuse anyone, looking like a charge. So that's just where it used to be. That's where it is now. And this creates a dipole oriented the same direction as the field. And the question is, how big is this dipole? Well, a good rule of thumb for most materials is that the dipole is just directly proportional to the E field. Now that makes some sense since we said that it tends to be in the same direction. But this alpha factor here, which is called the atomic polarizability, is sort of an interesting quantity. So what we're going to want to figure out is how big is that alpha. So we're talking about this dude alpha, not the most important constant ever to find structure constant, but this atomic polarizability constant. And we want to know what are some typical values for this. And how people express it a lot of times is in this sort of reduced alpha, where we divide by our favorite constants from electrostatics, so we can report alpha over 4 pi epsilon 0 for a few different atoms I picked out for you. So for hydrogen, for example, the number is 0.66. For helium, the number is 0.2, 0.5, and for carbon, the number is 1.67. Now the units of all these are times 10 to the minus 30, and in this case, in meters cubed. That's because we've reduced it by these constants. Normally, the units of electric polarizability are in coulomb meters squared per volt. But that all gets canceled out and gets changed into just meters cubed. So with some of these numbers in mind, let's do a problem. Okay, what we got here is we have an atom. Let's say it's a hydrogen atom. And we've put it in between two capacitor plates. Now let's connect them with some voltage applied across it. Now that voltage will give us an electric field oriented across the plates, and we want to say what is the effect on our atom. Now we can write down this useful relationship that the dipole moment is equal to alpha times E. But what we'd love to know is what is going to be the corresponding shift, little d, in the position of the atomic nucleus. What is the amount that this atom will deform? So to do that, we write our other definition of the dipole, which is just charge times distance, elementary charge. So we can equate that to alpha. But if we just have these capacitor plates charged with the voltage V, we can write down V divided by the separation of the capacitors, X. So rearranging all this, we get alpha V over E times X as our separation distance. Now let's plug in some numbers. Let's say we want to apply a pretty strong field, so we'll make the voltage 500 volts. And let's do a reasonable separation. Let's say 1 millimeter is the distance. And just for reference, the distance across an atom like this is about an angstrom. So 10 to the minus 10 meters. So if we plug all those values in, given the alpha for the hydrogen atom, we got from the previous page the separation distance D between the nucleus and the center of the electron density is going to be about 2. 10 to the minus 16 meters. That is a tiny number. That tells us that the deformation from even a very large electric field is going to be very small. So the atoms are not going to change very much in response. We're going to get tiny dipole moments resulting from tiny shifts in the charge distribution. So a related question that we could ask is, how strong does this voltage need to be in order to ionize this atom? Now what does that mean? That means it's strong enough to completely rip apart the nucleus and the electron of this hydrogen atom. So for that to be the case, the separation distance would have to be at least R. In our simplified model, that means pulling the nucleus all the way to the edge here, leaving the electron density behind. Now if we return to our simple statement, charge times distance, now R is equal to alpha times the voltage over the separation distance. So in this time solving for the voltage, we have it's equal to the separation distance times the charge times the atomic radius divided by the alpha. Now if we plug in the atomic radius as half an angstrom, separation of a millimeter, fundamental charge of a proton or an electron, and we use the atomic polarizability of a hydrogen atom, we get that the voltage would need to be 10 to the 8 coulomb per meter, which is just precisely equal to 100 million volts. That would be a huge electric field. Not likely to happen.